Hello YouTube. Today we're going to continue looking at the philosophy of SETI, and we're going to focus on the Drake equation, one of the most famous ideas to come out of research on extraterrestrials. But just before we get to that, I suppose to sort of set up a bit of the background, I think probably the most common argument for extraterrestrial intelligence is the ancestor of the Lucretian argument. Now, of course, these days we would disagree with many parts of Lucretius's cosmology, but the general form of his argument can be restated in modern language. We believe that life and intelligence arose here through purely physical processes, and there are so many stars in our universe, just like our sun, so many opportunities for intelligence to emerge. It's hard to see that it could only have happened once. Arthur C. Clarke once said, and I quote, "The idea that we are the only intelligent creatures in a cosmos of 100 million galaxies is so preposterous that few astronomers today would take it seriously." And I see this kind of argument pretty much any time the subject comes up among lay people. Now, this argument makes a very elementary blunder, the blunder of one-sided estimation. The trouble is that, for all that's been said so far, the probability of intelligent life arising around any given star may be extremely small, so small that it overwhelms the vast number of stars that there are. The number of stars in the observable universe is finite. Let's call it number n. If the probability of intelligence arising around a given star is less than 1 over n, then we're likely alone. Roy Mash, in his article Big Numbers in an Induction, has a nice thought experiment that really drives this point home. In the context of SETI, we're interested in finding extraterrestrial intelligence, but suppose, what's the probability that the observable universe contains extraterrestrial intelligence that speaks English? Well, that now is starting to look pretty implausible. Or what about extraterrestrial intelligence that is precisely the same as us in every single way, that's molecule for molecule identical, a twin Earth? I mean, obviously it would be a bad argument to say, well, hey, it's possible for a twin Earth to exist, so given the billions of stars in the universe, it must have happened somewhere. The problem is that the probability of an exact repetition of this planet is just too small. So clearly the point here is that in order to estimate whether there's intelligent life in the universe, we need to know more than the size of the universe. We need to know something about the probability of intelligence arising around a given star. And I mean, this leads us to the Drake equation, one of the most famous developments in SETI. Now, the Drake equation was proposed in the early 60s by the astronomer Frank Drake at a conference at Green Bank, and I think this really represents the point at which modern SETI was born. The Drake equation really defined the way that people have thought about these kinds of issues ever since. Drake was interested in the practical concern of actually discovering extraterrestrial life, of perhaps receiving extraterrestrial signals, say. And so the Drake equation concerns the number of civilizations in our galaxy. Presumably civilizations in other galaxies. Other galaxies are just so far away that even if they were producing signals, we probably wouldn't detect them. So the Drake equation concerns, it's a way of estimating the number of civilizations, communicating civilizations in our galaxy. And the equation looks like this. That may look a bit complicated, but don't worry, it's actually very simple. So what does this mean? Well, we have n. N represents the number of communicating civilizations in our galaxy. And then this is equal to all of these other factors that you then multiply together. So R star is the rate of star formation in the galaxy. Fp is the fraction of stars with planets. Ne is the number of planets per planetary system with habitable environments. And actually note that on Ne, although it says number of planets per planetary system, this really means planets and moons, because obviously it's conceivable that a moon could be habitable. So What we're really looking for is the number of large rocky objects, massive enough to hold an atmosphere, but not so massive that they end up becoming gas giants. So that's NE. FL is the fraction of habitable planets on which life has developed. FI is the fraction of life-bearing planets on which intelligent, civilized life has evolved. And FC is the fraction of civilizations that develop means of interstellar communication. And of course, this doesn't necessarily mean that they intend to communicate. It would be enough for the signals to be produced as byproducts of other activities. In the past, broadcast television transmitted millions of watts into space at very narrow bandwidths, and that should be fairly easily detectable by other civilizations. Broadcast television, we weren't intending to signal, but we were. So FC is number of civilizations that have signals going out that could be detected. And L, finally, is the average length of time during which civilizations release detectable signals. Now, if you multiply all of these factors together, you get N. You get the number of communicating civilizations in our galaxy. So, unlike the more popular ancestor of the Lucretian argument, this isn't just an appeal to large numbers. We're trying to actually work out what's the probability of a civilization, a communicating civilization, arising around any given star. Now, there are a couple of things to notice about this right away. First, this equation concerns the probability of us actually detecting an extraterrestrial civilization. It was designed in the context of SETI research, where we're looking for evidence of civilizations. So we need to know the number of civilizations that exist now, not just that existed a long time in the past. This is why Drake took the rate of star formation rather than just the number of stars, because civilizations will take a lot of time to develop. They're likely to be at different stages of development depending on the age of the star. So the point is, we're trying to figure out, well, how many civilizations are actually out there now that we might be able to detect, and that's the number we get from these factors. However, Andrei Kukla points out in his book on extraterrestrials that if we're interested in the probability of actually discovering, detecting another civilization, which is the goal of SETI, the Drake equation is incomplete. Because we also need to add the probability of two other factors. So first we need to consider the probability that any signals sent out by these extraterrestrials will be detected by us. Presumably, even during the time that a civilization releases signals, it won't release them continuously over the entire sky, and so their signals may not reach Earth. And even if their signals do reach Earth, we may not be looking in their direction. And in any case, they may not be broadcasting at a frequency that we're looking at. So, even assuming a kind of radio communicative species, there are all kinds of reasons why we just might not detect their signals. Also, there are various hypothetical means of communication that would simply be beyond our technological capacities to detect. There are hypothetical particles called tachyons that travel faster than light. Obviously, this is ruled out by current physics, but we might be wrong, and if such particles do exist, maybe extraterrestrials could communicate with them. Obviously, we wouldn't be able to detect that. A second factor we need to add is we need to know the probability that we would be able to recognize their signals as signals. So, even assuming we detect the signals, we might end up interpreting it as some purely natural phenomenon. I mean, it's at least conceivable that we could receive a signal but end up interpreting it incorrectly. So we would need to know these. We need to think about the probability of these other two factors to know how likely it is that we would detect another civilization out there. Another point about the Drake equation, which makes it a rather useful equation, is that we can formulate different equations for different propositions concerning extraterrestrials. For example, if you want to estimate the number of planets harboring extraterrestrial life, well, you take R star times FP times NE times FL times L star, where L star is the average length of time during which life exists. This equation might be relevant to the more general search for life, if we're interested in searching for life by looking for biosignature gases, for example. This modified Drake equation can be used to guess at what our success, what the potential for success here might be. The most important thing to note about the Drake equation is that the values for many of these terms are highly speculative. SETI researcher Bernard Oliver described the Drake equation as, and I quote, "a way of compressing a large amount of ignorance into a small space." So it's probably best to think of this equation as it's a tool for telling us what we don't know. Now we do have a pretty good idea for the first two terms. So the rate of star formation and the fraction of stars with planets, these are increasingly well understood. We don't really need to go into the technical details here, but the point is these are very favourable for extraterrestrial life. We know there are many stars. The estimates of star formation rate range from 1 to 16 per year. Any of these values is obviously promising. The galaxy is clearly full of stars. Furthermore, we know that many stars have planets, possibly almost all stars have planets. We're actually in something of a golden age of exoplanet research. We've found thousands of exoplanets in just the last few years. And so planets are very common. So that's good. That's looking good. The third term, the number of planets, that should be number of habitable planets per planetary system. Apologies for that, but that's obviously important. So the number of habitable planets per planetary system. Again, this is fairly well understood, broadly speaking. I have a couple of videos on planetary habitability that you might want to check out, but to sum it up, it does seem like a fairly high number of planetary systems will include habitable planets. We know that the basic building blocks of life, water, carbon, amino acids, these are abundant throughout the galaxy, so most planets will contain the basic elements of life. Now, a central concept in astrobiology is the circumstellar habitable zone. The habitable zone is the zone around a star where the temperature is just right that surface liquid water can exist. So I'll put up a graph of this. I should just note before I show you the graph, astronomers classify stars according to their spectral characteristics, according to the characteristics of the light produced by the star. And the classification is OBAF-GKM. And that's essentially a temperature sequence. O stars are the hottest at about 40,000 Kelvin. M stars are the coolest at around 3,000 Kelvin. Furthermore, at least for most stars, this is a mass sequence. So the O stars are the most massive. The M stars are the least massive. There are some exceptions, but for stars in the main stage of their lives where they are generating energy by nuclear fusion, this is a mass sequence where the O stars are the most massive, M stars are the least massive. The Sun is a G-type star. This graph shows the habitable zone for different types of stars. Unsurprisingly, you can see that as the stars get hotter, the habitable zone moves out. However, for a planet to be habitable, presumably the star also needs to persist for quite a long time. One of the big problems with the more massive stars, the O and A type stars, is although they're bigger, although they have more fuel, their greater mass and so greater pressure in their interiors means that they burn through the fuel more quickly. O stars only live a few million years, which isn't even enough time for planets to cool, let alone develop life. For complex life, certainly, we presumably need billions of years. So we can probably rule out the O, A, B type stars. As for the smaller stars, say M type stars, well, about 80% of all stars in the galaxy are M stars. M stars could live for hundreds of billions of years. So time is no problem, but they do have other issues. They tend to be much more violent than larger stars. They have intense solar flares that could sterilize a planet. And the habitable zone is so close to the star that the planet in it could end up being tidally locked. So it would show the same face to the star, which means obviously the heat from the star would be very unevenly distributed around the planet. I explain all of this in the planetary habitability videos. The important point is that most astronomers think that F, G and K stars will be the most conducive to life. That still leaves us with tens of billions of stars in the galaxy, and it's estimated that about 1 in 5 such stars have a rocky planet in the habitable zone. Now, of course, just because a planet's in the habitable zone, that doesn't mean it's habitable. It might have lost its atmosphere, or there might have been a runaway greenhouse or whatever. But still, we're looking at a lot of planets here. Furthermore, habitability almost certainly extends beyond the habitable zone. The habitable zone only concerns surface life. It's about whether there could be liquid water on the surface. But even within our own solar system, well, it seems pretty likely that Jupiter's moon Europa is in principle habitable. Europa contains a huge ocean of liquid water underneath a layer of ice. That the forces from its interaction with Jupiter provide the heat that prevents the water from freezing. Furthermore, it's believed that Europa's ocean interacts directly with its rocky core, which would allow it to become very rich with minerals. So simple microbial life, at least, could probably survive on Europa, so it would be habitable. A more recent idea is the galactic habitable zone. The idea is that some parts of the galaxy are fairly inimical to life. The centre of the galaxy is very dense with stars, which means a high chance of nearby supernova events and a higher chance of stellar encounters. So there's a higher chance of stars passing close by each other, which could cause planets to be disturbed from their orbits. On the other hand, away from the galactic centre, metallicity declines. So in astronomy, a metal is any element other than hydrogen or helium. Obviously, metals in this sense are required for life. So away from the galactic centre, you find increasingly lower metallicity, which would make it increasingly hard for life to develop. So it looks like we're looking at the kind of mid part of the galaxy, away from the centre but not too far away from the centre. So in general then, how many habitable planets does our galaxy contain? Well, probably quite a lot. Chris Impey in The Living Cosmos suggests that even on the most conservative estimates of the factors relevant to habitability, there are at least 25 million habitable worlds in the galaxy. That's probably far, far too low. There's probably a lot more than that. On the most optimistic estimates, if we think that planets around M-type stars could be habitable, and if we include cases of moons like Europa, that there are tens of billions. Whatever the precise details are, the situation is looking pretty good. The point is there are many, many abodes throughout the galaxy that could potentially host life. Now, these first three terms of the Drake equation, these are straightforward empirical matters. It's just a matter now of gathering more evidence, but this is basically just, as I say, just empirical, just a matter for scientists to work out the details here. The other four terms, however, are extremely controversial, and they're really just a matter of conjecture. We simply don't have a good theoretical understanding of any of these factors. So we have Fi is the fraction of habitable planets that develop life. Okay, we just don't know. We do not know what the probability of we don't know what's involved in the origin of life. So we can't really say what the probability is of a habitable planet developing life. Fl is the fraction of life-bearing planets that develop intelligent, civilized societies. Fc is the fraction of civilized societies that develop means of interstellar communication. and L is the lifetime of civilization. We'll discuss all of these in later videos. And also then there's the question of whether we could detect and then recognise a signal. I might discuss that later in this series as well, although I do actually already have a video related to that called Could We Communicate with Extraterrestrials? Anyway, the point is, as I say, these factors are all conjecture at this point, and we have to bear in mind that if just one factor in the Drake equation is unknown, then the prevalence of communicating civilizations is unknown. So even if you know all of the other factors with near certainty, and even if you know that they're all very favourable, again, if just one factor is unknown, we can't say how many communicating civilizations there are. And the problem for these last four factors is there's a huge range of answers that are supported by plausible arguments, right? And actually, I'm kind of curious what your intuitions are about these. I mean, if you had to guess, what numbers would you give to these factors? Before we go on in the series and discuss the arguments, what's your intuition for these four factors? What numbers would you put on them? I'd be quite curious to know that. So anyway, let's consider two examples of answering the Drake equation. So here's the first example of an answer. Some of these figures might seem optimistic, but I don't think any of them are unrealistic. There may easily be 3 planets or moons per star with habitable environments, if places like Europa turn out to be habitable. The high probability of life that I've got here, so that the FL at 0.99, that might look implausible, but many scientists actually have thought that life does emerge that easily, that life emerges basically as soon as conditions permit it. Carl Sagan, for instance, held this view. He thought that once you've got a habitable environment, life pops up. Then there's the high probability that a civilization develops interstellar communication, so I've got FC at 0.9 there. Well, humans have had complex societies for about 10,000 years at the most, which is a flash in astronomical time. So, arguably, once a species develops complex social organisation, technological development rapidly follows. As for the lifetime, could a civilization last 100,000 years? Well, many people have thought so. Many people have thought that the scientific, technological and moral development will solve our problems and allow us to live in relative peace without destroying ourselves. It's perhaps an optimistic vision of the future, but I suppose it's possible. In fact, many people have thought that once technology gets going, civilization should persist almost indefinitely, maybe millions or billions of years. So if you have these kinds of numbers, then we end up with the conclusion that our galaxy contains over 200,000 communicating civilizations. And bear in mind, N is not an estimate of how many civilizations have once existed or will exist in the future. This is the number that exists right now. Our galaxy is about 100,000 light years in diameter, so if those figures are right, it's teeming with intelligent civilizations. Let's try again with more pessimistic estimates. More pessimistic, but again, not unrealistic, right? I mean, these numbers could be right, given what we currently know. In fact, many people writing on the Drake equation have given far lower estimates for some of these factors. But on these estimates, as you can see, we're already probably alone in this galaxy. Most galaxies will be barren of life. So more than anything else, I suppose this little exercise illustrates the limits of Drake's equation. By varying our estimates of the factors within what is plausible given our current knowledge, we end up with very different answers. When Drake originally proposed his equation at the Green Bank conference, very optimistic estimates were made, with the result that there would be hundreds of thousands or even millions of civilizations in our galaxy. So at the time, people were very optimistic about the prevalence of extraterrestrial life. But this optimism fueled a famous argument known as the Fermi Paradox. Now, Fermi proposed this argument before the Drake equation was formulated, but it's especially pressing in the context of the high estimates that were made on the basis of the Drake equation. So basically, the problem is this: it's not really a paradox, strictly speaking, but you know, it's a problem. Interstellar travel appears to be technologically possible in principle, with spaceships travelling at, say, 1% the speed of light, which seems to be achievable if we extrapolate current technological trends into the future. I mean, 1% the speed of light is at least in principle possible. So travelling at 1% the speed of light, we should be able to colonise the galaxy within about 10 million years. But the galaxy has existed for billions of years. If intelligent life is common, we must be a very young civilization, right? Almost all civilizations would be older than us, millions or billions of years older. At least some of these should have traversed the galaxy by now. And presumably many of them would have been attracted to our solar system. They would have seen that the sun is a suitable star for life, which contains a planet in the habitable zone, a nice rocky planet with lots of water. So why aren't they here? If intelligence arises frequently, then many civilizations will have had the time and ability to explore the galaxy and ultimately colonize our solar system, but they haven't. And this implies that civilization is very rare. Michael Hart, in his article, An Explanation for the Absence of Extraterrestrials on Earth, has stated this argument especially forcefully. So Hart says there are basically 4 other explanations for the absence of extraterrestrials on Earth. Obviously, one explanation is there just are no other extraterrestrial civilizations. Hart says there are 4 other explanations. First, there is the possibility that interstellar travel is just not feasible in practice. Now, the primary difficulty faced by any civilization that wants to travel through space is the enormous distances and the correspondingly large travel times. But Hart says there are numerous solutions to this. Extraterrestrials might have developed the technology for suspended animation, allowing them to essentially hibernate during the flight. Or they might have produced the technology to produce substantial extensions to the lifespan. If you have a lifespan of 5,000 years, then a 300-year trip on a spaceship doesn't seem like such a big deal. Or they might structure the trip so that it occurs over many generations. If the ship is large and comfortable, people could live and die on it. There could be like a whole society on a large spaceship over many generations. Finally, you might just send probes or robots, self-replicating machines. Now, there's no need to go into the details here, but you can look up interstellar travel on Google. There are proposals that seem to be plausible. Assuming that technological development continues, in principle, at least, interstellar travel does seem to be possible. And after all, only a century ago, space travel of any kind was mere science fiction, and we've now sent people to the moon. We've sent probes right out to Pluto and further. Who knows what we might achieve with another century's progress. In any case, even if the vast majority of civilizations fail to develop interstellar travel, it only takes one. Remember, our optimistic values for the Drake equation gave us over 200,000 presently existing civilizations, and a similar number will have existed over billions of years into the past. So, we've had hundreds of thousands of civilizations existing for billions of years, and can we really suppose that not one of them develops interstellar travel? That interstellar travel would be impossible for all of them? Is that plausible? Hart thinks not. Second, Hart says there are sociological explanations. These include claims such as extraterrestrial civilizations are not interested in colonizing the galaxy, or civilizations tend to destroy themselves after developing technology like nuclear weapons, Or perhaps the galaxy has been colonised, but the extraterrestrials are choosing not to reveal themselves. Maybe they're treating the Earth as a kind of zoo or wildlife preserve that they're choosing to stay away from. So there's a whole class of explanations that appeal to the sociological features of the extraterrestrial civilizations. There's some feature of those civilizations whereby they choose or become unable to colonize. Not to colonize, rather. So Hart argues that the basic problem with all of these explanations is that civilizations are all different and civilizations constantly change. Any sociological explanation can only explain why some particular civilization at some particular time has not visited the Earth. But he thinks it's extremely implausible to suppose that such an explanation would be true of every race of extraterrestrials at every stage of their history after developing space travel. And furthermore, we should bear in mind that we have only one example of a technological civilization, our own, right? And obviously none of these sociological explanations are yet true of our civilization. We haven't destroyed ourselves yet. And we are interested in exploring the galaxy and in making contact with extraterrestrials. Hart says it's just unreasonable to assume that we would be unique among the alien civilizations, that there would never be another with our desire to explore and to make contact. In general, it seems to be a feature of life, that life is something that seeks out new resources, new habitats. And civilizations are, well, they require enormous energy input. There's certainly a lot of pressure to seek new resources, and the most abundant resources are out there among the stars. So so Hart thinks it's just unreasonable to think that any kind of sociological explanation could apply to all civilizations that have ever that have ever come into existence. Third, there is the explanation that extraterrestrials have not had time to reach us. Now, as already noted, the galaxy could be colonised within a few million years, but it's existed for billions. So Hart says there's more than enough time for colonisation, especially if civilization is common. The fourth explanation is that extraterrestrials have come. Extraterrestrials have visited the planet. I guess this one is popular among the UFO believers, the X-Files type stuff. The aliens are here and they're abducting people and probing them. That's not taken very seriously among astronomers. Slightly more plausible version of this is that extraterrestrials might have visited in the distant past but then left. If you had visited Earth a few billion years ago, there was nothing here but microbes. Maybe it wasn't a very interesting planet, or maybe the atmosphere wasn't right, or whatever. But Hart says, well, this still leaves the question of why these extraterrestrials left no trace of their visit, and also why no other extraterrestrials have come since to set up a more permanent colony. Why has nobody visited in the last 50 million years, say? The Earth would be a good site for colonisation. So here we end up having to appeal to the sociological explanations. Right, in order to explain, right, well, why did the visitors leave no trace? Why has nobody come back? Why have no other civilizations come since, etc.? We're going to have to appeal to sociological explanations, which Hart has already dealt with. So Hart concludes that the best explanation for the absence of extraterrestrial civilizations on Earth is simply that they don't exist. Humans are alone. I guess to sort of sum this up, Hart's basic argument is that there's a tension between two propositions, right? The proposition that there are many extraterrestrial civilizations, and the proposition that our descendants will probably colonize the galaxy. And the key point is that if you expect that civilization will eventually be capable of colonizing, then if there are other civilizations, if there are many other civilizations, some of them will already have colonized. But obviously they haven't colonised because they're not here. So that's essentially the Fermi Paradox. Now notice an interesting corollary of Hart's argument is that if there are many extraterrestrial civilizations, then probably we will never colonize the galaxy. None of the other civilizations have managed it, and we have no reason to think that there's anything special about us. So finding signals from extraterrestrials would perhaps be quite depressing, because it would imply that life never expands out into the stars. Nick Bostrom has recently developed this argument in his discussion of what he calls the Great Filter. He points out, since no civilization has yet colonized the galaxy, there must be some filter. There must be one or more highly improbable steps somewhere on the path to a colonizing civilization. So imagine you lay out all of the Drake factors, and then you add a term for the fraction of communicating civilizations that develop the capacity for interstellar travel. Well, one or more of these must have an extremely low value. It's a great filter, because with all the billions of starting points, the billions of stars in the galaxy existing for billions of years, we end up at the end with 0 colonizing civilizations. So somewhere along this path there is a filter that means we end up getting reduced to 0. No colonizers. Now suppose the Great Filter is in our past. In that case, it's extremely improbable for a civilization of our level to arise. Right, so we're probably alone. At least there might be extraterrestrial life, but we are this kind of technologically advanced society. This is the only one. Perhaps, for example, the origin of life was an extremely improbable event. We don't really know what's involved in the origin of life. We don't know how that happens. Maybe there's some process there that is just extremely that just requires extremely precise conditions that hardly ever obtain. Or perhaps the extremely improbable event was the development of intelligence. For the first couple billion years, life on this planet was entirely microbial. It took a very, very long time before complex multicellular life developed. So maybe life is prevalent throughout the galaxy, but Earth is unique in hosting complex life. Now the point is, if the Great Filter is behind us, and of course there's unlikely to be any advanced civilizations. That's Hart's conclusion, and we will be alone. But what if it's ahead? Well, if the Great Filter is ahead of us, then there is something that tends to prevent civilizations at our level of technological development from progressing further, from progressing into interstellar travel. The galaxy might be full of technological aliens, but they are forever tied to their own star. Maybe interstellar travel is technologically impractical, maybe advanced civilizations destroy themselves, whatever. Hart, of course, dismisses such possibilities, but it's speculative. We don't really know. Anyway, if the filter is ahead, then we can expect that we will never colonize space. Whatever it is that has prevented every other civilization will probably prevent us as well. So obviously we would probably hope that the filter is behind us. So Bostrom says we should hope that we actually don't find extraterrestrials. If we were to discover life on Mars or Europa, for example, well, that would fairly conclusively show that the origin of life is not improbable. It's happened twice in the same solar system, so the Great Filter can't lie there. If we discover complex life with signs of rudimentary intelligent behaviour, let's say we discover fish swimming around on Europa, well, again, that eliminates a much larger number of locations where the filter might be. It becomes increasingly probable that the filter lies ahead of us. As Bostrom says, the more complex life we found, the more depressing the news of its existence would be. And of course, if we pick up signals from an extraterrestrial civilization, that's worst of all, because then there's no question that the filter lies ahead. Civilizations like ours are common, but they they never get off their home planets. Of course, the filter could be both behind and ahead of us. There might be many filters. Bostrom's point is just, if we were to discover extraterrestrial signals, that would pretty much guarantee that it's ahead. And discovering complex life, say on Europa, would increase the probability that it's ahead. But if we search extensively and everywhere we go is barren, well, we can at least be confident that the filter is behind us. Maybe there's another filter ahead, but we can still hope that we will develop the ability to explore the galaxy. So that's an interesting little argument there. Most of us, I think, would be very excited about the discovery of extraterrestrials, but Bostrom says if we think about the implications of Fermi's paradox, it would actually be very bad news. Okay, so that's all for this video, and we'll continue this shortly. Thanks for watching. Goodbye.